as it says up on the screen, bust a few myths. There's a lot of stuff out there on the internet, on the interwebs about magnetic loops, some which is quite valid, but a lot which is not valid. Or there's a lot of things out there which you sort of go, really? So what I'm trying to do tonight is give you a bit of an idea about magnetic loops as an antenna. They're an interesting antenna. You've got to think a little bit differently about antennas, and you've got to sort of come to grips with them to use them effectively. But once you come to grips with them, I hope by the end of this presentation you'll see what the advantages are. And as part of it, I want to actually try, and I have actually sacrificed the presentation goat this morning. So I'm hoping that the few demonstrations that I'm going to try and make actually work. So, and I'm hoping that they demonstrate what I'm talking about. So let's get underway. Okay, firstly, apologies to Adam and Jamie, because I'm actually busting some myths. What I'm trying to do, and the myths I'm trying to bust tonight, are any old coaxial wire will do, any old capacitor will do. My loop is DC to daylight, can receive everything, can transmit on everything. A little bit about Jekyll and Hyde, and I hope you'll get a bit of a feel as to why it's the Jekyll and Hyde. And when you design a loop, you are always walking that bandwidth and efficiency tightrope, and I hope I can demonstrate why. A bit about what we're about to go through as well. So now, we've all heard about ChatGPT, the AI. And guess what? It was actually not bad, because it was about what I was actually going to say. The key thing here is highly selective. It is directional, but there are some issues with it being directional. It's narrow together, and I'll demonstrate why. Used for all sorts of applications, and the way it gets its name, magnetic loop, is it's a loop of wire. It's like a magnet, and that's how it actually couples the magnet and the electrical, so electromagnetic wave. So it does it slightly different to your dipole or equivalent. So I actually left this in here. That's what ChatGPT came up with, and it wasn't bad. So I thought, okay. Now, I just want to do, there's a definitional thing here. I'm talking about STLs, not STDs, STLs. Small transmitting loops. Now, the definition of a small transmitting loop is, it's a loop which is greater than 1/8 of a wavelength of what you're trying to receive and transmit, and it's less than 1/3 of a wavelength. And the reason for those two is when you transmit on something that's between these two, you end up with uniform current distribution around the loop, which means you get a uniform radiation pattern. When you go outside that, all sorts of things start happening. So I'm talking about a small transmitting loop in this sort of characteristic. So what I did was put in 80 metres and 20 metres, and into the website, which I'll show you in a few slides' time. And what it comes up with is, for 80 metres, you're talking about, and this is circumference. So this is circumference, obviously. For an 80 metre loop, you're talking about a circumference of about 10 metres. Now that's a pretty big loop. That's actually a pretty big loop. If you go up to less than just 1/3, you're up to an absolutely huge loop. Natural resonance. Now, this is the resonance of a loop which is this sort of size, is somewhere between 9.5 and 4 megs. So, okay, that's getting pretty close. It's got a bit of capacitance and it's got a bit of inductance, obviously. And if we come down to the other end of the HF spectrum, is same thing, but you'll see natural resonance. This is 10 meters, so this is 28 megs, but the natural resonance of that sort of size loop is up in this sort of area. Absolutely fascinating. So STL, it's just a big inductor. So think inductor, but this inductor transmits really well. Okay, this is the technical bit of the talk. Lee Turner, who unfortunately is silent key, from the Adelaide Hills Amateur Radio Society, wrote a number of papers around magnetic loops, and they came from Professor Underhill in the UK. They actually, Professor Underhill came out and did some talks for Adelaide Hills, absolutely fascinating talks about small transmitting loops. And Lee then took that information and developed it. And his version 2 paper, which I'll distribute all of these links and everything, is an absolute wealth of information. Ah, yeah. Turn up the 2. Yeah. See, I always forget something. Absolute wealth of information. And the title that I put in here is read it, and read it again, because each time you read it, you get something else out of the paper. So he makes a comment, which I highlight. Narrow instantaneous bandwidth rather than poor efficiency is the fundamental thing limiting factor when you design a small loop. You either get bandwidth or efficiency. And it's one of those engineering compromises all the time. And I'll demonstrate that in 2 slides' time. Electrically small antennas always suffer from being narrow bandwidth, whether they're verticals with loading coils or they're combinations, trapped dipoles or whatever. It's always an engineering compromise. And for loops, the key thing is minimizing what they call the lumped resistances, ohmic resistances. And as you lower those, you have to obviously raise the power to get the radiation level up to the same sort of level. It's much easier to find low loss capacitors than low loss inductors. So, and in this particular case, and I'll show you what's sitting in the top of this, there's a vacuum capacitor sits in the top of this. And yeah, okay, reduction of any of those ohmic resistances, whether it's your connection to the vacuum capacitor, it's the loop itself, it's the connection between them, and I'll show you how I've reduced this down. And in fact, thank you to Alan for lending me a 4-wire resistive meter, enabling me to actually demonstrate how low you can get if you try. So. Any old wire or valve capacitor will do the job. No, you've got to really work on it, and you've got to have that in the back of your mind. So I'm just going to say at this point in time, I think that myth is well and truly busted, and I'll demonstrate it with a table in a sec. Read it, and read it again. There's a whole lot of things that come out of this paper. At resonance, all the power applied to the loop will be radiated except for your losses. So if you get those losses down as low as you can get, more power gets radiated. There's a little bit about how it actually radiates. I'm not going to go into that. The radiation resistance is so low with a loop. Now, the radiation resistance, I've got to get this right. The radiation resistance in relation to an antenna is the imaginary power that you put into the antenna to overcome what would normally be dissipated as heat in an antenna. And so it's an imaginary, it's a number that enables you to measure how much power that antenna is actually putting out. So in relation to a loop, that radiation resistance is very low. And so to get the same level of power out, you actually have to increase the power in. So critically dependent on achieving really high Q in the hundreds and the thousands. And I'll show you how high Q this particular build has delivered. Now, the interesting thing in this paper, Lee makes this comment. He says, a small transmitting loop carry current uniformly around the loop. And in fact, if you maintain those less than a third or greater than an eighth, the current is uniformly distributed around that loop. Now, in theory, that loop shouldn't radiate. Think about your inductors in circuits. Inductors don't radiate. If they did, your circuit you'd have all sorts of problems. However, there are just small phase differences between one side of the loop and the other, which actually causes the loop to radiate, which is good, because then it's an antenna. So there's some real nuggets of information out of this paper. Now, Tinder for mag loops. You need to both swipe right to couple. No, sorry. Some people in the room get it. There's a whole lot of ways to couple the transmitter into the loop. There is your shielded Faraday loop, and this is actually what Steve uses in his loop. The unshielded coupling loop, which is what I actually use, which is this one here. And I'll show you some pictures on how that's connected. Then there's the gamma match. And in fact, I'll try and demonstrate an interesting effect of gamma matches where you add in some human capacity. And then there's another way of doing it, which is through toroidal loops, which you actually put around the center. Now, the key thing here is it has to be in the center of the loop. If it's not in the center of the loop, your radiation pattern won't be uniform. So toroidal loops right in the center, and then you have some loops of wire, or you have one of these loops, either shielded or unshielded, through your toroidal core. The last one is that I haven't got a picture of here is a series capacitor. So you actually put a series capacitor in the middle of the loop. At this point, there's zero voltage. The top, there's a lot of voltage. And I'll show you the chart that makes it a bit scary. So you put a series capacitor at the bottom. The problem with series capacitor is it's very narrow bandwidth. So whenever you change frequencies, you actually have to change the coupling capacitor. So it gets a bit painful. So, and yeah, all of these came from Lee's paper. So this is one area, and I make the comment, definite experimentation. I've just got an unshielded loop, which is great, and I've been able to match reasonably well to it. But this is an area where I think I can improve the performance even more of the loop through some experimentation with different coupling methods. So that's a definite future plan. If there's any questions, please jump in. Okay. Now, VK3 CPU, Miguel, has come up with a wonderful little app that enables you to visually show all the different parameters of a magnetic loop. And you can put in down here, there's a little loop down here, little model loop, and it enables you to go, okay, I've got a loop of about, now it's the top one. For this particular loop, that is LDF 750, which is 46.4 millimeters in diameter. So there's 46.4. Then enables you to put in the loop size. And if I come back to somewhere like where this is about 4.2, I reckon it is. It's around about there. Now, each one of these coloured lines is each of the parameters. So you've got your capacitor, the voltage that capacitor has to withstand, the bandwidth in kilohertz, the efficiency of the loop, your ohms, your reactance, what's that one? Your Q, the number of the current going through the loop, and the wavelength of the loop. What I was able to do down here at the bottom is this is the ohmic resistance. You can see it changing here. Now, I was able to get through silver soldering, and I'm using 46% silver solder, which is the most silver solder that you can, silver solder that you can get. I was able to silver solder on to the ends of the bit of coax, and I'll show you that in a sec. The plates that then connect to the vacuum capacitor, and on measuring it using Alan's wonderful 4-wire resistance meter, I was actually able to get down to 0.0023 of an ohm between one connection to the vacuum capacitor and the other. When I looked up the characteristics of the coax, that's exactly the characteristics of the coax. So I couldn't get it any lower. I got it down to whatever the characteristics of that particular coax is. So I can't go any lower. However, what happens if you can't? Now this is, I can use any old coax or any old piece of wire, can't I? Here's what happens. So I'll increase the resistance. Now the key characteristic that we're looking at here is this line here. This is the efficiency in percent. And here's 50%. So the rule of thumb is if the antenna is efficient 50% or more, it's not a bad transmitting antenna. Now, this is 40 meters. This is 40 meters, the one end of 40 meters and the other end. And then we go to 30 meters. And then, what is it, 17 meters? No?
That's 20 meters. That's 20 meters.
20 meters, no, that's right, correct. And then we go to 18 megs, and then we go up to 15 meters. And it's both ends of 15 meters. So let's increase. Let me just try and jot that down just a fraction. There we go. Now, watch what happens as the ohmic resistance increases.
Wow.
There goes 40 meters. There goes 30 meters. Now, we're at 0.072. I'll keep going. Let me get down to maybe 1 ohm. Now, some weird stuff happens in the middle here, but I'm down to 0.255 of an ohm. And you've dropped out, you've got an okay for meters, for 18 megs, for 20 meters, but the rest of them have dropped off the scale for not much change. So it's worth getting that ohmic resistance, doing whatever you can to get that ohmic resistance down. Now, the other thing here is, what about the difference between copper and aluminium? So let's click aluminium. What happens? Oh, not much. The interesting one that changes though is this curve here. That baby poo yellow, that's the voltage on the vacuum capacitor. So it goes all the way up. This is kilovolts. So this is 1, 2. This is up to 7 kilovolts at the top. So you're up at about 6 kilovolts. Down here at that's 40 meters. So at 40 meters, you're about 6 kilovolts. So your vacuum capacitor has to be able to take 6 kilovolts. 100 watts. So 100 watts is down here. Sorry, I've worked on that. Good point, Rex. 100 watts. You can drop that power down if you want to, and you can see the voltage and everything comes down. So you can limit it that way. The size of the loop. This is an interesting one. The form factor of the loop. So a circular loop versus an octagonal loop versus a hexagonal loop versus a square loop. Now, the difference between these, there's very little difference between ones that are sort of semicircular. But when you go to square, notice 15 meters dropped off for the same size loop. You actually have to change the size of the loop to get 15 meters back. So I thought that was an interesting little characteristic. But the thing about this, and I'll put a link to this website, if you put in VK3 CPU and mag loop, you can play to your heart's content. And just down below here, you'll find all of these little symbols. It tells you what all these little symbols are, the inputs through the sliders, etc., etc. But absolutely fascinating. Now, I managed to get the vacuum capacitor from the Meet the Voice boot sale. So it was a 4 to 200 picofarad vacuum capacitor. So I'm able to put in the parameters in here to give me about 200 picofarads at this end and about 8 picofarads at this end for a 15 to 40 meter loop. Now, the key thing with that is, if I want to transmit on this loop and get anything near and above 50%, they're the parameters that I can put in. And that's what I designed the loop for. So I designed the loop around the vacuum capacitor that I had. For those who don't know, vacuum capacitors be expensive if you want to buy them. And so if you can get hold of one, you're probably designing your loop around that. That's the primary design factor. So, okay, now let's just try and find my cursor again.
Did your loop work to 15 meters?
Yes, and it works very nicely to 15 meters. Well and truly. Okay. Well and truly. And in fact, I'll demonstrate. I have taken some sweeps with the Nano VNA, and I'm hoping, if the presentation gods are good to me, I'll be able to. Now, how do I get rid of that? Let's minimize that. Lovely. So, size of the tube, I showed that. Actually, no, I didn't show that. Sorry. I didn't show the size of the tube, did I? What the size of the tube actually does. Because this is almost 50 mil, 2-inch tube. So here's the size of the tube. So hang on, let's make it circular again. No, that's aluminium. Let's make it circular again and change the size of the tube. So let's go down to really small tube. So as we go down, okay, actually this is going up in frequency. This is not bad. There's a few other things happening in here. The radiation resistance is heading up fairly scarily. We've got, that's 20 metres. So we've come down 20 metres. Anything below 20 metres, forget it. You're below that 50%. Now, let's go in the other direction. Let's make it bigger. Okay, we're coming back to, and we're at 46.5. Oh, sorry. Bottom one, Justin. Sorry. Now, as we come down in size, we've got the Q's going up for the lower frequencies. Now it's going down. We've got the efficiency now starting to come down. Anything below 20 metres, that's it. And we've got up to almost 24 megs. Oh, okay. So let's go up in the other direction. So we're up to where we were with this loop at 46. Okay, that's where we are right at the moment. Now, let's get this at, hang on, I'll just get this back to where it is. 4 point, there we go. Okay. Now let's go bigger in size. So bigger tube. Efficiency's coming up slowly, absolutely slowly, until we get to what, about 67 millimeters, and we've got a voltage that's gone up fairly dramatically, and everything becomes about stable after about 70 mil, which is interesting. Now 70 mil tube, I wish you luck, but I have seen some loops made out of the tubing that they use for ventilation, which is actually, I think it's alfoil, it's aluminium around the outside. I've seen some loops made out of that, which are the sort of this size, and that's one of the reasons they do this. But past about 70 mil, doesn't change very much, and you don't get much advantage with this sized loop. Now, what happens to the capacitance? Yeah, it's about the same, 186. So I'd be able to do it with that particular capacitor. Up here, it's about 17.8. So yeah, so it's the thing about this. It enables you to model what you're trying to do. And yep.
Does it allow for different forms, different shapes of that material? Like, for instance, if you were to make this out of rolled RHS, can you change it to square rather than round in that? Parameters there?
Well, you can certainly.
No, that's the
The actual form factor of the aluminium. No, it doesn't. It certainly doesn't. It just assumes that it's round, and I'm not sure. Not sure how much that would change, because what it's looking for is, this is a surface effect that it's looking for. So if you increase the size, you're actually increasing the surface area. So it's so long as you're keeping that sort of surface area, I suspect it won't change very much. But I stand to be corrected, well and truly. But
Justin, in terms of you're measuring the DC resistance of the coil,
correct.
Is that valid when you're dealing with the radiation from the surface?
Interesting point. I assume it is, because they actually take into account the expected radiation resistance from having this ohmic resistance in the calculation.
It'd be quite different if you made a solid, but if you could make a solid piece of copper, the DC resistance would be less. Would be much less. The surface resistance.
Well, and I made a point a bit earlier. magnetic loops, where you get it down to this sort of level, the radiation resistance is so low anyway, it doesn't, I don't think it would change that much. But interesting point.
I don't know anyone can afford to make that.
Well, and also, but correct, and you'd have to deal with a whole lot more weight. Solid copper of that, it wouldn't be PVC pipe, I'll tell you now. So yeah. Yeah, actually, you're probably right, Brian. You're probably right. Because you'll notice up the top there are bits of cutting board. That's what it is. It's bits of cutting board which actually make sure that the relationship between the two ends stays the same and doesn't try and rip the vacuum capacitor apart. So yeah. So I hope I've busted the myth of the DC to daylight. It depends on size of the loop, your vacuum capacitor, what it can cover, etc. So
Question on that.
Yep.
Does that mean, for instance, you can have one loop that works from 40 metres to 10 metres,
Yep.
but you need another one if you want to go from 180.
Well and truly. You design for that whatever you're wanting to design it for.
Into the 1/8, 1/3 measurements, you can't go outside those, so your frequency range is limited by that.
Upper all bands.
But Rex, it begs the question. There's these wonderful, and I made a fairly offhand comment, and I apologise for it on the Discord channel. Somebody, in fact, I think it was Lance. Was it Lance? No, was it you? Talked about the shielded loop. Somebody asked a comment about the shielded loop for a receiving antenna, and these are sold as DC to daylight receiving antennas, and they're actually active antennas because they've usually got a amplifier in the bottom of them. And I come to the conclusion that about the only advantage it's got is it's directional. But it might as well be a piece of wire in the air with an amplifier on it. That's
Contact.
correct, and they do use them for direction finding antennas. So but that's about the only advantage you get from the antenna. So yeah. So anyway, so I think I busted the myth, but I'm happy to be corrected. Now, this is the chart I was talking about. This is the chart from the VK3 CPU modeling software for this loop. Now, what I've done is it was designed specifically for the tuning capacitor, which is from 200 to 4 picofarads. So this is great. 40 meters. Efficiency's down a little bit, but okay. Q's fantastic. Now, Q's really, really high. So I'm expecting the bandwidth to be quite narrow. In fact, down to not quite SSB. Band pass. Whereas you go up to 15 meters and we're down, okay, can still cover it, fantastic. And we're at 82 or 80 up to 89 at the other end of 15 meters. So fantastic. Mind you, I thought, Rex, this is okay for WSJT.
Yeah.
Yep.
Sure.
A piece of cake. And in fact, you might even be able to do correct. And I specifically put in 3.5 megs in here. Wasn't designed for that, but just to give you an idea. So down here at 80 meters, your efficiency is down here. You've got to have a vacuum capacitor that goes to at least 700 picofarads. And they'd be expensive if you want to go from 700 to zero. Efficiency's down. The bandwidth is down to 1 kilohertz. So it certainly operates down here if you've got a capacitor that goes down there. But that's the key thing around. It's all being lost. It's all going. It's all being lost. So Q, bandwidth, efficiency. You're playing all of these. You're well and truly playing all of these. Now, so the stuff I did to hopefully try and imitate the parameters I've been talking about. Here's the end of the coax. I silver soldered around here on the inside and the outside these copper brackets that for the vacuum capacitor. There's the vacuum capacitor that in the actual brackets. Coupling loop is just connected. There's a bit of 9913 that goes to an N-type, and it's literally an unshielded loop. A bit of LDF 450, I think it is. Yes, it's half an inch, and there's a ratio that a 1:5 ratio, which that's not quite 1:5, but there's a 1:5 ratio between the surface area of your coupling loop to the surface area of your main loop, so that you have the most efficient, or the ability to get the most efficient coupling. Some of the other bits and pieces. That's my 100 to a 50 mil coupling loop. Now, you would expect when you buy a 100 to 50 mil coupling loop that ends 100 mil and this ends 50 mil. Who would expect that?
No.
They're plumbers millimeters. So I ended up having to machine a flange to go in there, which was good because they wouldn't have published the review, I reckon. So there is a flange that now fits in there now, which is good because, and hold that thought, there's some other stuff coming. The coupling here is to a bit of dowel. That's to the end of the vacuum capacitor, and at the bottom, which is sitting behind this cover here, is a 12-volt geared motor with a little mechanism with 2 micro switches, so it doesn't overdrive the vacuum capacitor one way or the other. So, and then it's all 100 mil pipe.
So you've got a rod going all the way up to the plastic.
Correct, and it's a wooden rod, could be, but so it's not affecting it at all. Now, so testing it. This is Alan's wonderful device telling me that it's 0.0023 of an ohm. The 3 is up for debate. So I was able, and this is me actually measuring it at the connections to the vacuum capacitor. So it's making sure that these bonded joints are actually as good as I can make them, and that's the 45% silver solder. And that's LDF 750 specification says that it's 0.525 ohms per 1,000 meters. If you scale that down to 4 or 4.3 meters, it's that. So that was the 20 meter. This is the 40 meter. So you can see now, the key thing here is have a look, based on the scale down the bottom, have a look at the width of that loop, because that's bandwidth. So 7 megs, you've got, that's 7, that's 7.115. So there's a reasonable amount of bandwidth. You'd be able to, that's SSB, not a problem. We go to 30 meters. Now, slightly different scale. So we've got this is the scale for this. So it's slightly wider, but so that's a wider curve. Good SWR though.
Where's the 2 to 1 mark?
Sorry?
There's no 2 to 1 mark. We've got no reference.
Just go a little bit
Go
longer,
straight from 1 to
halfway
5.
between 1 and 5, and you'll have it.
Yeah.
Okay. I'll wear that. 18 megs. Now, this is the same scale. I got this the right scale. But you'll notice as we go up in frequency, bandwidth is increasing as well, because that loop is actually going quite wide. The 300 odd sample points is showing that as we go up in frequency, the bandwidth is getting higher and higher, which is what the design specifications were telling us. So that's a demonstration of it. So this is where I was talking about the Q being the Jekyll and Hyde, where the higher the Q, the lower the bandwidth, and you've got to have a careful balance of what you've got in the way of a capacitor, what you've got as the characteristics of the coil to basically land where you want to land and get the bandwidth you want with the quality of the coil. So that's the Jekyll and Hyde that I was talking about. And so that's the other myth bust that I'm suggesting. Now, how does it perform in real world? I've had this for the last fortnight on Whisper, 5-watt Whisper around the world. Now, I'll just point out, this is from, I think this might have been from yesterday or the day before. 0W10DW. It's a balloon.
Oh.
Now, I don't believe this because it's 0.005 and it's 18,373 kilometres. If the grid square it was reporting is right. I actually don't believe that's right. But that's actually a balloon.
That's fine.
Big difference.
It might just be true because you remember that aircraft
You never know.
go a long way
Negative
because there's no interruption.
You only got one spot.
Plus
I know, only one spot.
Yeah.
Which I just go, nah, this is just not. But 0.005 of a watt and it's +5. Now, what I think happened here is if that was going over, the grid square didn't change. It was misreporting the grid square. But interesting pickup. But so I just wanted to point out this is what I'm getting with 5 watts. I make the comment here over it's about 10,000 Whisper points in a couple of days. Over that period and over that number, I'm getting about 50% receive and 50% transmit. So it's being received 50% of the time. So my transmit signal is being received 50% of the time, and I'm getting 50% of those results. So I've come to the conclusion that the transmit and receive performance of the loop's pretty reasonable. Actually, pretty reasonable. For those who don't know, there is WhisperNet, which is where all the Whisper records go into, all go into a database on WhisperNet. Now, Phil Barnard, VK7JJ, who's a very smart cookie, has actually got a website called whisper.rocks. It's a very Phil thing, that does a whole lot of Whisper analysis. And it does it on huge data sets. So I went to his site and so this is the last fortnight of me transmitting and receiving from Phil's website. That's 18.3 thousand kilometres. That's not bad. It's the highest one. It's all of Europe. It's into China. It's into Japan. It's into Russia. And it's obviously North America and Europe and a few.
You want to go out north?
Well, that's Greenland. That's somewhere out in the middle of nowhere. None down here in Bouvet Island or wherever it is. Anyway, wasn't in that period, they'd gone. But that's the last fortnight. So on 5 watts from that, pointed at about I think it's about a 200 degree bearing. So reasonable performance. I have had some lots of FT8 contacts and lots of SSB contacts as well, with good reports. Now, this is for Rex. One of the charts that Phil's website has is a propagation reporter for the last 30 days. Now, to be able to come up with this chart, the data set behind this is huge. Each month, there is something like about 10 or 15 million lines added to that database each month. And so to try and manipulate that is something momentous. This is the 23rd and 24th of March, which is where we had a wonderful auroral display. And it also really affected all of the HF bands because there were much, much less reporting at that period. So I put that in for Rex. But there are a whole lot of other charts available on VK7JJ's website. Please, please, please have a look. It's free. If you go to whisper.net, whispernet.org, it has a link in the left-hand side for whisper.rocks. In fact, it's the first one of the analysis websites. Okay. Presentation gods again. This one, I'm actually going to, I can guarantee this one's going to work. What we have is, this is 20 metres. Can we all see what that waterfall's doing? Don't need to, just need to see colour.
Want me to hold it up?
Oh no, that's all right. That's. Now we're going away from it. Let's come back. Now we're coming back into the passband of where we're tuned to. Oh, here comes the noise. Coming up. It's really coming up now. It's going past. Notice the red line? That's the passband that we just went through, the bandwidth of this loop at 20 metres. Now, the key thing to mention there is when you get it tuned to the right, like about there, where you're in the most noise, you're also in the most signal, but you're not hearing anything either side of that. Well, very little. Sorry, that's not a correct statement. Very little of what's next to it. So I just wanted to demonstrate that's the bandwidth arrangement of the antenna on a waterfall. It very much. I've got the reference up fairly. Oh, I see. But
There on the wall.
so now this will be fun. This will be fun. We're on. Actually, what I might do is just bear with me. We'll put. There we go. Here's my little mini key. I'll get somebody to push the key for me. Now put it in the right hole, Justin. No. Okay. Can somebody push that key for me and keep it down? Now, all this is a ferrite rod with a couple of coils of wire on it and an LED. So I can actually show, you notice, see the LED? Now, if I come around here, it's lit up. I come around here. Oh, it's gone out. I keep going around here. Nothing. No. Oh, yes. Okay, we're back on again. Now we're only putting 10 watts through this, but you can actually physically see the radiation patterns off both sides. So, thank you, Brian. So a really handy device. I used to use that for my 630 metre transmitter. I knew not to touch the antenna when that was lit because it bit. Alan's laughing. So yeah. So just to show you that radiation pattern, and I've actually got a radiation pattern. We're on the home straight now. So the Jekyll and Hyde, the Q and the bandwidth. And I've just demonstrated it. So walking the bandwidth efficiency tightrope, you got a really low bandwidth. Efficiency's down low as well. You've got design issues. And you get down to here and you've got much wider bandwidth, much lower Q too. That's why you've got wider bandwidth, and your efficiency is actually pretty good. Not bad at all. So, myth busted. Okay, just a few, this is the last couple of slides. One of the things I was put onto by VK7ZPD up north was there was a wonderful little project by Dave Truen, G7IYK, which is a magnetic loop tuner. Now, the way that he's actually done it is really nice because there is actually a really sensitive SWR bridge built into this, and it sits there and tunes your loop, so varies the vacuum capacitor up and down, and keeps it at its best, so its lowest SWR, whilst you transmit away, so you don't have to worry about it. And you can also manually tune as well. So really, really nice bit of kit. It gets over the whole thing of having to do this the manual way, which is just an up and down. Just all that's doing is reversing the polarity on the motor in here. So that's and fantastic support for it right at the moment, because I've got a problem with it right at the moment, and Dave is actually helping me out. Phil's helping me out, and a few other people. So that's good. The other thing is you need a rotator. The radiation pattern is at the lower frequencies is a donut this side and a donut that side.
It's
off the ends. So it's now the problem with that is it's off both ends. So how do you know whether it's long path or short path? I'll leave that to you thinking about.
Question from
Yeah.
a lot I've read suggests that the broadside null is really more useful for nulling out local interference, not so much for directivity of the antenna. Tommy?
Interesting. I have to say I probably haven't had enough experience in using it like that. So what I might do, it's very warm in here. Put that on. I actually don't know. I don't think I can answer that. I haven't had enough experience with using it. No. Well, it's spot on. I've certainly played with nulling out noise, which is one of the benefits of it. You can, but the other, you balance that. Nulling out the noise is great, but if it's not pointed in the right direction, you're not actually firing off in the right direction. So
I think what they're getting at is the amount of gain off the ends isn't necessarily a lot higher than it is, say, off 45 degrees, for instance.
Yeah,
Very much the same, actually.
Correct.
Donut.
And
it's the same amount of gain in every direction except through the null.
Through the null, well and truly. And at the lower frequencies, it is radiating in all radiation angles,
Yeah. Straight down.
straight up and straight down. So you're for a good DX antenna, you're wanting low angle radiation in the direction you want. Well, you get it, but you get it in all other directions as well. And you also pick up in all other directions as well. So there's a balance. You've got a bit of directivity, but yeah, I don't know. I don't have enough experience.
Okay.
So.
Well, that's the conventional wisdom out there, is that the broadside null is really about nulling out local interference.
Yeah. Which is great if it's in the right, if you then end up firing off in the right direction. Ish. Now,
I don't have enough experience either.
Ask me in 6 months' time. Now, the other thing, obviously, it's directional. You need some sort of rotator on it. The rotator only obviously needs to be 90 or 180 degrees. I'm intending to use, this is a K3NG rotator, comes from Remote QTH. So that's what I'm actually using to drive the rotator. Okay, key things. I mentioned silver solder and copper straps. The widest diameter tube you can afford. The highest range and the highest voltage vacuum capacity you can afford. I actually used carbon paste around the top and the bottom of the vacuum capacitor, because I was finding that the dissimilar metals were, as soon as it got any sort of moisture outside, they were starting to corrode. But there's a whole lot of other products that are available. In fact, this is what Tas Networks use on all their high voltage connections. And careful construction and waterproofing. So now, who knows Trevor Briggs, VK7TB up in, yeah. This is Evandale or Launceston?
I think he's moved.
Oh, okay. Yeah. Now, Trevor designed a beautiful magnetic loop that uses all of the principles I've been talking about. It's actually a 2-loop arrangement, and I'm not quite sure what Trevor does, whether he's phasing those in some sort of way or they're actually connected in some way. But this is on a big rotator. It rotates at the bottom. A very nice vacuum capacitor, which is very high range from one end to the other. You can see these are copper straps that are connecting to the loop. The loop is aluminium that's about this in diameter, that he's had folded up. Sorry?
I was going to make a comment. It actually blends in with the garden really well.
Oh, it does. He probably says it's a sculpture. Yeah. Coupling loop and the coupling arrangement that he's got. There's some mechanism down the bottom, which I'm not sure what it actually does. I think that might be some sort of phasing arrangement between the loops. I don't know. And that's what it looks like with somebody standing next to it. So yeah. But fantastic. And I have to thank Trevor for these shots, and also Idris, who sent these shots to me. This is when they were actually putting it into Trevor's garden. So, okay, advantages and disadvantages. That's at the lower frequencies, that's the pattern that I'm talking about. That's the loop through there. As we go up in frequency, that becomes less. It becomes more like this. It's small. It's small. It can be portable. That came in the van tonight. It's directional. At those lower frequencies, it's all radiation angles at once.
It works very well close to the ground.
There you go.
Doesn't need to be very high off the ground at all.
Not affected by the ground very much at all. So that would only be affecting the radiation pattern, that wouldn't it?
I'm not sure, but they do work relatively close to the ground.
Yeah. Okay.
One diameter off the ground is all they need.
All they need. Okay. Narrow bandwidth, it's hearing the signal at the bandwidth. It's also hearing the noise at the bandwidth, but it's only hearing that bit of the noise, not this much of the noise. So, yeah. Now, challenges. Finish off with, it's long and short path at the same time, so I'm not quite sure how you know that. I haven't had enough experience to know that. Oh, correct. You're constantly having to retune. This gets over that because it's doing it for you. Retuning between bands is pretty slow. You saw how long it took to move that across the screen. That's a little 12-volt motor in there, absolutely screaming through a gearbox. But you don't want it any faster because you miss it. You miss the peaks. So you've got to balance that. Some people, and this will drive a stepper motor as well as a DC motor. Some people put stepper motors on them. Yeah, lower efficiency means power is not radiated. Lower bandwidth may limit the modes that you're able to actually use down at those really low, low efficiency, low bandwidth parts of the loop. Okay, what's next? It is being permanently mounted. There's a weatherproof jacket that goes over it, that zips up over it to stop water ingress in the bits that shouldn't have water in them. I'm looking at a 6-metre loop right at the moment, actually, with a PEX trombone.
Yeah.
This is the Jim Tregellis plastic fantastic PEX tube, and I know Steve's built one.
And they work really well.
When you say 6 metres, you mean 6 metre band or
6 metre band? 6 metre band. Yeah. Now, there's a very interesting idea by this guy, and I'll put the link in the notes. He uses PVC pipe and aluminium tape. I'm a little bit dubious about how he gets the resistance down, but his vacuum capacitor arrangement, instead of a vacuum capacitor, he's actually got a tube which has the aluminium tape on it that he moves up and down the PVC pipe to tune it, which is quite an interesting idea. It's a square loop. Interesting idea, but I'm still a bit. It's out on whether he can actually meet some of the requirements I've been talking about. The thicker copper plate, I think, and that's more about structure and strength than anything, than less resistance, and the coupling. I need to do more work on the coupling. Now, I received this text message from my wife in the middle of the day. And in fact, Sean here walked up to me just as I read it in Hobart, which was, please don't freak out, but I'm very sorry that your antenna's blown over in the wind and broken. And all I said was, so this is when we had those gusty winds. Now, I didn't have any weight on the base, that was my fault. It blew over and it broke at the weakness, which is the hole here, which you'll notice now is screwed up, which it wasn't screwed up when this happened. So I rebuilt it. And as you can see, fortunately the vacuum capacitor survived, but I had to do some dent knocking on the tube. Anyway, so it took me an afternoon to rebuild the tube, and so it did work reasonably well because I knew exactly what I needed and the improvements I was going to make. So the slots in there and the holes in the tube are much smaller. They're the minimum size. Lots of thank yous. I'll just point out, Steve, VK7 SFA, who has a absolutely great call sign there, the 160 metre loop design, which was in AR magazine, fantastic bit of work because he goes into all of these arrangements. Steve has built one and in fact tested the resistance last week.
Yeah, include the results.
So yeah, and have a look at whisper.rocks. Fantastic website. And the references. Okay, any questions? Or anything you want me to demonstrate again? Oh, there you go.
Justin,
Yeah.
changing the shape of the coupling loop does what exactly around it?
Okay, that would affect the coupling efficiency because what the coupling loop does is the surface area of your coupling loop is intersecting with the surface, the radiation pattern of your actual or your, yeah, the radiation pattern effectively. So I'm not sure it would cause the efficiency to go down, but your radiation pattern may be affected. Not sure about that.
Can I make a comment there, Justin?
Yeah.
Some people squash the loop in order to increase the surface area contact between the two loops to improve the efficiency.
Okay.
The position of the coupling loop also has an impact on the SWR or your impedance.
Correct.
So you can adjust it around until you get the correct impedance.
Well and truly. And in fact, I've done that. I've actually brought it closer to the loop to improve the SWR. And that was to improve the SWR at the lower frequencies. At the higher frequencies, it was fine. The coupling was great. But at those lower frequencies, I actually brought the where the coupling is closer to the loop, and it improved things. Not much. You're talking about quarter of an inch, quarter to half an inch. Not much.
And the next question is, does a variable capacitor remove the need to change out the coupler?
I'm not sure of the question.
No, I'm not either.
The variable capacitor is the frequency determining element. The coupler, like in its current form, I'm getting pretty reasonable SWR across each of the bands that I want to use it on. So I'm happy with it, but I'm also aware that it could probably be even better with either a gamma match or a shielded Faraday loop.
Yeah.
So
to comment on from personal experience, I have used a magnetic loop where the resonant frequency, which is what you're tuning with the capacitor, was not the lowest SWR point. That was some distance away because of the way the thing had been constructed.
Yep.
So the position of the inducting loop is affects your impedance, but the capacitor affects your resonant frequency.
Yeah. Okay. Cool. Thanks, Steve. None.
Given this is a magnetic radiator, how are you approaching your calculations to satisfy the ACMA?
Well,
Another nature.
where it's ending up is actually on about a 4 or 5 metre pole, well and truly away from everything. So, yes, I'm certainly about that question, but interesting question.
It is very much more critical.
No, correct.
Even quite moderate antennas at magnetic radiation far exceed the expected safety level.
Yep.
I mean, it's all bullshit, but
yeah. No. But you're right. You're spot on. And my answer to that is it's further work in progress.
just putting like
On there.
You certainly keep away from the top of the loop, because the top of the loop is where that chart, the scary voltages are, and why you need a vacuum capacitor that can actually take those voltages.
Here's the interesting thing, Justin. If you go on the web and have a look at other people's design, they often have them upside down. They have the capacitor at the bottom. And the two reasons for that. One is that because that's where all the weight is.
Yep.
And so it's not practical to build a magnetic loop with the capacitor at the top without sufficient support.
Correct.
And the other reason is that a lot of people do manual tuning, and so they want that easy to get to.
Yeah.
But that's where the scary voltages are.
I'll let that do it. And that's why the scary voltages are well away. There is a piece of wooden dowel that comes all the way down to here. So everything is away from the top of the loop.
When you dowel goes with it.
Well, interesting question. I originally thought it was going to be fiberglass, but at the time, I had a piece of dowel at the ready. So, yeah.
You get a piece of that plastic from Venetian blinds. So
Well and truly, lots of different ideas. I haven't now. This is Steve asked me a question a little while ago. He said, once you've got this loop up and going, please put a piece of conductive material up the middle of it and see what happens to the loop.
Aluminium would be nice.
I haven't done that yet. It'll be interesting to see what it actually does, because if it doesn't have that much of an effect, actually that's a much better and a much stronger supporting mechanism.
I suspect a steel pipe would be no good.
Yeah.
From a magnetic point of view, it would absolutely destroy the pattern. But aluminium, I'm not sure.
So yet to be tried. Yet to be tried. But anyway. So if there's no more questions, what I'll do, please come up. What I'll do is take those covers off so you can actually see inside. And yeah, and have a play. The 705 sitting here. You can change the bandwidth and see it go past and all of that sort of stuff. So yeah, please have a go. Okay. But anyway, I change the frequency. Sorry, change the resonance of the antenna. That's correct. So I hope I've given you some information about magnetic loops that you didn't know before.
Everybody go and build one then.
thanks, Justin.
Cool.